Hello everyone, welcome to our discussion of section 3.7 where we will be talking about indeterminate limits using the L'Hopital rule. Well, just a little bit of a history as you can see on the screen. L'Hopital was a French mathematician who actually wasn't the person who came up with this method. Instead it was Johann Bernoulli, a Swiss mathematician, that came up with it, but L'Hopital paid him to name the method after him. So basically he bought the rights to it. So that's just a little bit of a history about what this method is. But the gist of this method is that sometimes when we try to calculate limit of expressions, we end up with these kinds of forms. You can see them on the screen. I think this is pretty much all of them, but I'm not sure. Maybe there's one or more, two other forms that came out to be where we have to use the L'Hopital rule. But if we take the limit of an expression and we end up with one of these forms, then we can apply the L'Hopital rule. L'Hopital rule is basically a method that breaks the expression up into segments, into fragments, and it applies the derivative to each fragment, and then it takes the limit of the derivative of those fragments. Now, having said that, putting an expression into fraction form, that is, if the original expression that we're trying to find the limit for, if it's already in fraction form, then we want to go about applying the L'Hopital rule to it, if applicable, in that fraction form. But if an expression is not in fraction form, and we end up with one of these outcomes, these limits, then we want to put that expression in fraction form before applying the L'Hopital rule. So having an expression in fraction form is key to applying the L'Hopital rule. And here are some examples of expression that give us one of these forms as we apply the limit to it. So this is already in fraction form, and if we substitute for x with 1, of course we end up with this form, right? 0 over 0, which makes it immediately a candidate for application of the L'Hopital rule. This one, we will come up with this outcome if we take the limit of it. So again, this expression is a candidate for applying the L'Hopital rule. But for this one, somehow we need to reduce this expression to either entirely in fraction form or partially in fraction form. But somehow we need to rewrite this. This is where a little bit of creativity comes in handy. To rewrite an expression that is not already in fraction form before applying the L'Hopital rule. That's one of the key aspects of applying the L'Hopital rule. The other aspect is that sometimes when you break up an expression into fragments, parts of it don't require the application of the L'Hopital rule. In other words, if you take the limit of one piece at, say, that infinity, it's not going to be one of these indeterminate forms. These, and I should highlight or underline this, we're looking for indeterminate form of an expression when we apply the limit. So sometimes a piece or a fragment of that expression is okay. In other words, if you take the limit of that piece, you end up with some kind of a limit that is not one of these forms. So for those parts of an expression, we don't need to apply the L'Hopital rule. But we still have to apply the L'Hopital rule to portions of the original expression that if you take the limit of, you end up with one of these indeterminate forms. Okay, so remember, those are the key features of applying the L'Hopital rule. We have to have either the entire expression or part of it written in fraction form, and we don't have to necessarily apply the L'Hopital rule to every part of the expression, we need to apply it only to the piece of the original expression where if we take the limit of, we end up with an indeterminate form. Okay? So having said that, then what is the L'Hopital rule? So here in this box, you can see I've highlighted it. So first, we take the limit of original expression as it is. If we end up one of those forms, indeterminate forms, then what we do, we take the limit of the derivative of the numerator, expression in the numerator, and the derivative of the expression in the denominator separately. That's why I mentioned L'Hopital applies itself to pieces of the original expression. So it breaks it up into fragments, takes the derivative of them, then applies the limit. So we wouldn't take, you remember when we talked about taking the derivative of a quotient, right? That's not what we're doing here. We're not going to take the derivative of the quotient. We're going to take once an original expression is in fraction form, we're going to take the derivative of the numerator separately and take the derivative of the denominator separately, then apply the limit after that. Now, sometimes it's possible that even after you take the derivatives of the numerator and the denominator and apply the limit, you still end up with one of these forms, indeterminate forms. If that happens, that's quite okay. We can apply the L'Hopital rule a second time. And if that doesn't help, if even after that the limit still gives us an indeterminate form, that's quite okay. We can apply the L'Hopital rule a third time and a fourth time if necessary. Okay, as you'll see, this is a very, very useful method. All right. On the next slide, you'll see what I just said at least a couple of times, which is a key technique when applying the L'Hopital rule is to write the indeterminate portion of the limit in fraction form. Okay, this piece is loaded with information. Write the indeterminate portion of the limit in fraction form. Okay. All right, having said that, let's begin going over these examples. So before I forget, when you see an example like this, please pause the video and give it a go on your own, maybe 15, 20 minutes, no more than 20 minutes, but spend your time on this. Write your solution down on a piece of scratch paper before you unpause the video and look at the solution that I have. Okay, that's key to your learning. If you just copy what I'm writing down, that's not learning. So 90% of learning is that you write down your solution and then you compare it with somebody else's. That's 90% of learning. And I trust that you'll do that as you go through this video. All right, so here if we apply the L'Hopital or the limit, not the L'Hopital, but the limit to this expression that we have, first we have to verify if we have an indeterminate case. Otherwise, we can't use the L'Hopital rule. So let us apply this limit to each piece of this. Right off the bat, notice that if you take the limit of this piece, cosine of x, at a plus, it's just going to be some constant value, right? Cosine of some, because cosine is a function, as we learned in trigonometry, has a domain that is negative infinity to infinity. So once we take the limit of this piece, we're going to end up with a constant. So this piece is not indeterminate. But if you take a look at the other pieces, the natural log of x minus a, for example, for sure we're going to end up with something that is negative infinity, right? We will have some number here in the argument of the natural log, which is very, very small, very, very close to zero. Therefore, taking the natural log of that, whatever that number, will be negative infinity. And if we plug in for x with a here, once again, we're going to end up with the same thing. So it's again negative infinity over negative infinity. So this piece of the expression is indeterminate. But let me write it down so you have this as part of the notes. So we have, if we take the limit of cosine, this piece, cosine of x, times the limit of the other piece of this expression. So notice I broke it up into the indeterminate piece of this expression and the part that is okay. And natural log of e to the x minus e to the a. Right? So we quickly see that the first piece, if we take the limit, it'll be cosine of a, and then times negative infinity over negative infinity. So this piece is the indeterminate piece of this, so that piece. So we can apply the L'Hopital rule to that piece. Okay. So by the L'Hopital rule, we have to take the derivative of the numerator and then the derivative of the denominator. Let me put the parentheses here. All right. So we have this first piece, it's okay. We keep it at that. Times limit as x goes to a from the right-hand side. So this is the derivative of the numerator, right? 1 over x minus a. By the chain rule, we take multiply this by the derivative of the inside, which is 1, so it makes no difference. And then divided by the derivative of this piece, which of course is 1 over e to the x minus e to the a times, by the chain rule, times the derivative of the argument of this natural log function, which is e to the x. Okay, like that. So now, let's clean this up a little bit. This is a complex fraction. Let's rewrite it so it's a little bit more clear what we have. So we have, in the first piece, we have cosine of a times the limit of, we can put this limit on the outside, limit as x goes to a from the right-hand side, and then we have e to the x. I've been teaching basic algebra for a long time, so part of me wants to explain what's happening here, but time doesn't allow us. You guys are in calculus, so you should be okay with this. But if you have any questions about simplifying the complex fraction, please let me know, or just come by my office hours. Okay, and then we have e to the x times x minus a. All right, and then so if we take we can distribute this e to the x again. So we have cosine of a times limit as x goes to a from the right-hand side, and e to the x minus e to the a. I'm just going to distribute this x times e to the x minus a times e to the x. Okay. So now, if we apply this limit to that, we will get an indeterminate form of a different form than that. So we will get, let me write that here, cosine of a times, so plug for x with a, we get e to the a minus e to the a, so we get 0 divided by a times e to the a times minus a times e to the a. Again, we get, so this time we get a, notice that the first time, let me highlight this, the first time when we got the indeterminate form, it was of this kind. Now we're getting, again, we're getting an indeterminate form, so we will need to apply the L'Hopital rule a second time. So let me just write that down, indeterminate form, apply L'Hopital's rule. Like that, okay? And this is the second time we're going to do that, like that. Okay, so then this time we're going to apply the L'Hopital rule to this piece, and we're going to leave this alone. All right, so let's, I should say, apply L'Hopital rule for a second time. Okay, so we end up with another neat little expression. And this time it'll be derivative of the numerator, it'll be just e to the x. The derivative of the denominator, that would be 1 times e to the x, which is e to the x, then e to the x times x, which is plus x times e to the x, and minus a times e to the x. Like that. Okay. Now, if we apply the limit, what will we get? Let's see. So we get cosine of a times, that will be e to the a in the numerator, right? And we're applying the limit. So we get e to the a, and then we get e to the a here, right? And then plus a times e to the a minus a times e to the a. Just plugging in for x with a every time we see x. So you can see what's happening here. These two guys cancel each other out. We end up with e to the a over e to the a, which is 1. Cosine of a times 1. So finally we have arrived at a result that is not indeterminate. So cosine of a. So that's the final result there. Okay. So very, very useful technique, this L'Hopital rule is. Okay. Let's look at another example. Before that, I have a quick note here. It says indeterminate products. So if we have if we take the limit of a product of two expressions like this, and it leads to this, 0 times infinity or infinity times 0. In such cases, we can write the product as a quotient, which is what I was saying earlier. So we need to rewrite that expression as a fraction before applying the L'Hopital rule. In other words, we can either write f over 1 over g, and this is again a complex fraction. If you simplify it, you get f times g again. Or we can say g over 1 over f. Which one will do depends on the expression we have and which way would it be easier for us to go. Either way, we have to rewrite that product as a quotient. Okay? So here we have an example of this kind. Again, please pause the video and solve this on your own before you compare it with this solution. I trust that you will do that. Okay, so I'm assuming you're done this and you're back. So usually, if you have a cotangent or tangent, it's easier if we rewrite them in terms of sine or cosine. But this is not always the case. Once in a while, it's better if we go the opposite. And if you have 1 over sine of x, it's better to write it as a cosecant of x. So 1 over sine of x is equal to a cosecant x, and 1 over cosine of x is equal to secant x, as you remember from Math 127 if you took trigonometry at UNLV. Okay, so I'm gonna do that here. I will put this in fraction form, so we have cotangent of 2x is equal to cosine of 2x divided by sine of 2x times the sine of 6 times x. Okay, and so now if we apply the limit, what will we get? We get 0 over sine would be 0. And so cosine of 2x, cosine of 0 would be 1 over 0. That would be undefined, right? 1 divided by a value that is getting closer and closer to 0. It would be infinity, but it would be undefined. Or we can show it as infinity times, of course, limit of this expression would be 0. So we have an indeterminate case, right? So this is an indeterminate form, and we need to use L'Hopital's rule. Okay. All right, so we're going to take the derivative of this, the numerator, keeping in mind, well, let me rewrite this. So I'm going to multiply this by the numerator first. I think it would be clearer if I do it that way. And so we have cosine of 2x times sine of 6x divided by sine of 2x, right? Nonetheless, we have converted this expression into a piece that has fraction, right? So that's the important thing before we apply the L'Hopital rule. Okay, so we're going to take the derivative of this, multiply it by that, and then take the derivative of sine of 6x multiplied by this, add it together, right? Well, let me do it actually. So limit as x goes to 0 is equal to, that would be minus, by the chain rule, we have to multiply it by this 2, right? So minus 2 sine of 2x, that times sine of 6x plus cosine of 6x times 6 by the chain rule, right? So 6 times cosine of 6x times cosine of 2x. And then, so that's the denominator of the numerator divided by the derivative of the denominator. So that would be 2 times cosine of 2x, like that. Okay. Now that we've done that, let's apply the limit again. What will we get? So we get, if we apply the limit to this piece, sine of 0 is 0 times minus 2 is 0. Sine of 0, 6 times 0 is 0, sine of 0 is 0. Plus 6 times, cosine of 0 is 1. 1 times 6 is 6, times cosine of 0 again is 1. So divided by cosine of 0, as we apply the limit, cosine of 0 is 1. 1 times 2 is 2. So we end up with 6 over 2, or the final limit, which is just 3. Okay. So you can see how much of a difference L'Hopital's rule makes, right? This is where we were with the original expression as we tried to take the limit of it as x goes to 0. But look at that. After applying the L'Hopital rule, we actually have the result converges on 3. Okay, that's a big difference from an indeterminate form to a number that converges to that. The limit that converges to that. Okay, very, very important. All right, so let's have a look at another example. This time, indeterminate differences. This is again, goes back to the original sheet. Let me bring that back, that slide back. You remember, we're going through some of these. So these are naturally, we can apply the L'Hopital rule, but these we're just talking about, okay, if we have this form, or 0 times infinity, which I don't see it here, but maybe I should add it. But that was one of the forms that we just had, the example that we just went over. But this next one is of this kind, which is again indeterminate case. Okay, so we're just going through these and looking at them specifically one by one. So indeterminate differences, that's if we have, once you apply the limit, and I should actually put here, it seems that I forgot, limit of this expression as x goes to infinity, right? So if we end up with that, then in such cases, we want to write down these in fraction and then find the common denominator, or find an equivalent fraction of some kind for the entire expression, or factor the terms such that we end up with a fraction. Any of these will work. Okay. So looking at this example, I just want to remind you to please pause the video at this point. Spend no more than 20 minutes, but spend your own time. Come up with your own solution, your own thinking. 90% of that learning in this course depends on your own thoughts, not mine. So my solutions are worthless unless you have your solutions written down already. If you've done that, then my solutions have value because you can compare them with yours. Otherwise, without your solutions first, my solutions are really are not worth much. Okay? So please solve this, and I trust that you've done that, and now you're back. So let's compare our solutions. So the first thing, we want to establish that this is an indeterminate form, right? So if we apply the limit, what will we get? We get infinity minus natural log of infinity, again, is infinity. So this is indeterminate form. We've established that. So we want to use the L'Hopital's rule. Okay. So in this case, if we factor out x, we will end up with a fraction. So let's use factoring. Using factoring or factoring this expression, we will have limit as x goes to infinity of x times 1, right? X times 1 is x, minus natural log of x over x. You see that? So factoring, we were able to generate a fraction. Now, if you take the limit of this piece, we will just get infinity, right? And that's not indeterminate form, right? If I look back at these, that in itself is not an indeterminate form. So, but if you take the limit of this piece, natural log of infinity over infinity, you end up with infinity over infinity, which is an indeterminate piece of part of this original expression. So this is the piece we want to apply the L'Hopital rule to, not that piece. Okay, so let me make that clear. So this is the indeterminate limit, and so need to apply L'Hopital's rule. But this piece is not indeterminate. So simply just plug in for x with infinity. That's not an indeterminate form, right? So we say no need to apply L'Hopital's rule to that piece. To that. Okay. So you can see how L'Hopital's rule, it looks at the original expression in fragmented form. It breaks it up into, or converts it into a fraction. Then it looks at different pieces of it. It looks for indeterminate pieces of it. And then it applies the technique to that piece only, not necessarily to the whole expression. All right, so we have applying the L'Hopital rule just to this piece. Okay, and I want to highlight that. Need to apply L'Hopital rule just to that piece, to that fraction. Okay, so what do we have? We have limit as x goes to infinity, x and times. So the other pieces stay as they are, x and then 1. Now take the derivative of the numerator, that's 1 over x. Take the derivative of the denominator, that's 1, like that, right? Now we apply the limit. What will we get? For x, we get infinity, and then 1 minus 1 over infinity divided by 1, right? Of course, that 1 over infinity is 0. Divided by 1 is 0, so we get 1 minus 0, or 1 minus 0. So we have infinity times 1 minus 0 over 1, 1 minus 0, or infinity, which is the final result. Okay. So if the limit, I just remind you what we discussed earlier in the course, that if the limit is infinity, it simply means that limit does not exist, but this is not an indeterminate limit. We're simply saying that if the limit is equal to infinity, then the limit doesn't exist. Okay. But this is not indeterminate form. All right, so let's look at another example. So again, we have, if we apply the limit, what are we going to get here? We're going to get, this is limit of this expression as x goes to 1 from the right hand side. So we get 1 minus 1, that's 0, natural log of some very, very, very small number. It's going to be negative infinity, right? So negative infinity, the same thing, minus infinity, that would be positive infinity, and that would be an indeterminate form. So let me write that down. So applying the limit first, we have to establish that we have a case that is a candidate, a valid candidate for the L'Hopital rule. That's what we're doing. So we have natural log of 1 minus 1 minus natural log of 1 minus 1. And we, of course, this is natural log of 0 from the right-hand side, right? Because this is this number would be slightly larger than 1. So the difference would be a positive, right? So we're approaching 0 from the right-hand side, minus the same scenario here in this other piece, approaching this result as we take the limit, approaches 0 from the right side. Okay, so what are we going to get? We're going to get negative infinity here, minus infinity here, or minus infinity plus infinity, or we can rewrite this and say positive infinity minus infinity, and that's certainly an indeterminate case, right? So indeterminate limit and we have to apply the L'Hopital rule. Okay. All right. So the first thing we have to do is, of course, figure out a way to rewrite this in fraction form. And because this is a difference of two natural logs to the same base e, right, we can easily apply the natural log properties and rewrite this in a fraction form, right? This is something we learned in pre-calculus or even college algebra, I think. So we write limit as x goes to 1 from the right-hand side of natural log of, let's put those in fraction form, x to the 7th power minus 1 divided by x to the 5th minus 1. So we're going to get natural log of, if we apply the limit, we're going to get, what are we going to get? We're going to get 0 over 0, right? So notice again we got an indeterminate form, but this is a different form. The first time it was like that, right? Now we have it like that. So this is again an indeterminate form. And I want to highlight that yet again. Indeterminate form. So we apply L'Hopital's rule a second time, and we can apply it as many times as it's applicable, a second time. Okay, so let's do that, which means we're going to go back to this expression and take the derivative of the numerator and the denominator. So let's do that. So we will have, let's see, so natural log of, let me put the natural log, we can put the natural log in front of the limit. So natural log of the limit of that expression as x goes to 1 from the right-hand side, and then take the derivative of that, 7 times x to the 6th power divided by 5 times x to the 4th power, right? And now, if we apply the limit, what are we going to get? And I want to underline a second time, okay? And so we're going to get natural log of 7 times 1 to 6th power, 5 times 1 to 4th power, and we have natural log of 7 over 5. There you have it. So we have our final result. Again, I'm sure you see the power of this. We were trying to take the limit of this expression. Originally, we got an indeterminate limit. And now, applying the L'Hopital rule, we were able to get a convergence. The limit of that expression, as x goes to 1 from the right-hand side, converges to this number, natural log of 7 over 5. So you can see the usefulness of that. Okay. So now of the other forms of the other indeterminate forms, we haven't yet talked about these, right? So 0 to 0 power, infinity to 0 power, 1 to infinity power. These are also indeterminate forms of one kind or another as we try to take the limits of expression sometimes. So in such cases, when we come across one of these cases, we may use taking the natural log of both sides. We need to take the natural log of both sides. When we talked about solving exponential functions in pre-calculus 1, you recall we talked about this, right, this technique. But at the time, we were not taking the limit. We were just solving for the x in the exponential function. So we're familiar with this technique, but we're just going to have to tweak it and apply it in conjunction with the L'Hopital rule, applying the L'Hopital rule. Okay? So this is how we're going to do this. Suppose we have an original expression like this that leads to one of these indeterminate forms. And then what we do, we set this piece, the expression itself, to y. Let y be all of that expression. After that, we take the natural log of both sides. Natural log of y equals original limit of natural log of this whole expression. Of course, that's going to bring, by the properties of natural logs, this is going to help us bring this power down and in front of this natural log, right? The thing that we have to be cautious about, very cautious about with this method, is that when we find the ultimate result, it's not going to be the limit of the original expression. It's going to be the limit of natural log of y. See, the original expression, we set it equal to y, right? So when we find the limit using this method, it's going to give us it's always going to give us the limit of the natural log of y. But is that what we wanted? No, we wanted the limit of y, right? That's what y is equal to. Y is equal to that, which is equal to the original expression. So we're really after the limit of y as x approaches some value. When you apply this technique, it's always going to give you the limit of natural log of y, not y. So what we have to do at the end, and this is what I'm saying this, convert to limit of this expression as x goes to a. That means this is what we have right now. Limit of natural log of y as x goes to a. But we want to convert this to the limit of the original expression. That's what this red ink is saying. So how do we do that? We simply take e and raise it to this power, both sides. E to power natural log of y, and by properties of natural logs and logs, we remember that's going to reduce that to y. Right? So e to natural log of y is equal to y. And then e to that is equal to the original expression, f of x to g of x power. Okay? E to natural log of y is equal to y. E to natural log of f of x to g of x power is equal to f of x to g of x power. We'll have to do this step every time we apply this method. We have to convert it back to the original expression. Okay, we have to remember to do that. All right, so let's look at an example or two. So again, please pause the video, spend 15-20 minutes on this, and after you're done, unpause the video and compare your solution with this. Okay, so I'm assuming you've done that, and now you're back. Well, let's apply the limit first to see what we'll get. We'll get 0 to square root of 0, or equals to 0 to 0 power. This is certainly one of those indeterminate forms, right? So this is an indeterminate form, and we have to apply L'Hopital's rule. Okay, so we're going to do that method step by step. First, we're going to have to set this expression equal to y. So let us do that. Let y equal x2 square root of x, right? Now we're going to have to take the natural log of both sides. So natural log of y is equal to square root of x, right? Natural log of x to square root of x power. And then, of course, this, by the properties of logarithmic expressions, this square root of x can come down and in front. So we'll have natural log of y. Do you see how we set y equals that, and then we're taking the natural log of both sides? See, at the end, the result is going to be for natural log of y. The limit is going to be for natural log of y, not for y. So we're going to have to convert it as I mentioned earlier. You'll see how that works. So square root of x times natural log of x, right? Now, if we take the limit of both sides, which is conditioned here, so we say limit of x, limit as x goes to 0 from the right-hand side of natural log of y is equal to limit as x goes to 0 from the right of square root of x natural log of x, right? And so eventually we have to take steps to put this right-hand side in fraction form. You know that, right? We need that before we can apply the L'Hopital rule. So, and because we're going to eventually take the derivative of this expression, let me rewrite this in power term. So I'm going to convert this to power term, and it's going to be starting from this side. We have x to 1/2 power times natural log of x. And then we have limit as x goes to 0 from the right side of natural log of y. Let me move this up a little bit. And so we can rewrite this in fraction form, right? So we can put this in the denominator with a negative power. So let's do that. We have limit as x goes to 0 from the right-hand side of natural log of x over x to minus 1/2 power. And so let's see. So we're going to, now we can apply the L'Hopital rule. On the left, everything stays the same. So we have limit as x goes to 0 from the right-hand side of natural log of y is equal to limit as x goes to 0 from the right-hand side. Derivative of natural log of x, it's 1 over x, right? And derivative of this is just minus x to minus 3/2 power divided by 2. So that minus is that minus 1/2 times that. Reduce the power by 1, and we get that. Okay. So if we clean this up a little bit, let's clean this up. So what are we going to get? We're going to get limit of natural log of y as x goes to 0 from the right side is equal to limit of 2, and the x's will simplify. We will get, and with this minus, we get minus 2 times square root of x. And if we apply the limit here, what are we going to get? We're going to get 0. Okay, so this is not an indeterminate result. This is a valid result. The limit we found, we applied the L'Hopital rule to this expression. We got that. Then we took the limit, we ended up with 0. This is a valid result. But remember, and this is so important, this is not yet the final answer. Because we took the natural log of both sides. So to convert this, actually let me write it down so you have it in your notes. So to convert this limit, we want to apply the natural exponential function. And let me write it in red. Apply the natural exponential function to both sides. Okay, so doing that, log. So originally this is what we have. This is what we ended up with, right? And then limit of applying the natural exponential function to both sides, we have limit e to natural log of y as x goes to 0 from the right. We have to do the same thing to the right, apply the natural exponential function to that. And what do we get? On the left side, we get just y, right? We get limit of y as x goes to 0 from the right. On the right side, we get 1, right? E to 0 power is 1. But remember, y was this, right? X to square root of x power, right? So we have, so therefore, we know that limit of that is equal to 1. We simply substitute for y with this expression, and the right side is 1. Therefore, limit of x, or x to square root of x equals 1. Like that. Okay, so just remember, to go from here to here, we have to go back where we set let y equal that expression. So we're replacing y with all of this. Replacing y with all of this equals that. All right. So I hope that makes sense. Let's look at another example. So in this case, we want to please pause the video and give it a go with your own solution here. Spend about 20 minutes. When you're done, unpause the video and compare your work with this. I trust that you're going to do that. So, and I trust that you've done that, and now you're back. So if we apply the limit to this, and we remember that natural or tangent of 2x is equal to sine of 2x over cosine of 2x, right? So if we apply this to that, we're going to get 0 to 0, which is an indeterminate form. So this is an indeterminate form. Apply L'Hopital's rule. Okay. Again, by this method, we set all of this equal to y. So let y equals tangent of 2x to x power. Then we take the natural log of both sides, right? And that'll bring this down, x times natural log of tangent of 2x. And so now we apply the limit of the original expression, right? Limit as x goes to 0 from the right of natural log of y would be equal to limit as x goes to 0 from the right side of x times natural log of tangent of 2x, right? Like that. So you know that we have to rewrite this in fraction form, right? Before we can apply the L'Hopital rule. So let's do that. Limit as x goes to 0 from the right of natural log of y would be equal to, we can put x in the denominator and say tangent or natural log of tangent of 2x divided by 1 over x, right? This is a complex fraction. If you simplify it, we get the x times that back. Okay? So now we can apply the L'Hopital rule. Applying that, and we have natural. Take the limit of both sides. So take the derivative of the numerator, which would be 1 over tangent of 2x times, that would be secant squared 2x times 2, right, by the chain rule. Minus, and the denominator, the derivative of that would be this. And limit of as x goes to 0 from the right, natural log of y. I'm just speeding a little bit because I think there's a class coming in. So if we rewrite this as tangent of 2x as 1 over sine of 2x over cosine of 2x, right? And then times, we write secant squared 2x as 2 over cosine squared 2x, all of that over minus 1 over x squared, right? So then we can then clean this up a little bit. Let's clean this up. Limit of, like that, of natural log of y on the left side would be equal to limit as x goes to 0 from the right of cosine of 2x divided by sine of 2x times 2 over cosine squared 2x, all of that divided by minus 1 over x squared, right? And then, so again, simplifying this a little more, we get limit of x goes to 0 from the right natural log of y equals limit as x goes to 0 from the right. I'm just cleaning this up, simplifying it. We get minus 2x squared cosine of 2x divided by sine 2x cosine squared 2x. Okay, that's, let me just double check to make sure that looks good. And then this is, so let me go to the next page. Here I'm running out of room there. So again, I picked up this speed because I think there's another class coming into this classroom. And so let's see. So on the left, we have limit of x, as x goes to 0 from the right of natural log of y, and that is equal to, if we simplify things, we get, so we have minus 2x squared, right, divided by this cosine of 2x, but with one of this cancels out, we get, of course, sine of 2x cosine of 2x. And then we have limit of, as x goes to 0 from the right, let's break this up. We break it up to 2x over sine of 2x times minus x over cosine of 2x, close bracket, and then we don't need that anymore. So now as we apply the limit to this, let me actually apply it to each individual one. Something interesting happens here. This one, we can rewrite it as 1 over sine of 2x over 2x, right? By flipping 1 over that gives us that back. So that times limit as x goes to 0 from the right of negative x over cosine of 2x, like that. And so we, and then recall that limit as x goes to 0 of sine of x over x equals 1. Remember that? So that means if we apply the limit, that we can apply this to that and we get 1. So on the left, we still have the limit of natural log of y as x goes to 0 from the right is equal to 1 over 1 over 1, or 1 over 1. This is just 1 over 1, sorry. I will clean this up before posting it on Web Campus. I will get rid of that, but that's just 1 over 1. And then times, if you apply 0, so 0 over 1, 0 over 1 is 0. So we get that. And that's equal to 0, right? But this is not, remember, this is not yet the final result. We need to convert it because this is the limit of natural log of y. We want the limit of y as x goes to 0 from the right side. So we need to apply the natural exponential function to both sides. So we take limit as x goes to 0 of e to natural log of y equals e to 0 power, right? So we raise both sides to natural exponential function. On the left, we will get limit of, as x goes to 0 from the right side, y, right? That simplifies to just y equals 1. Okay? So remember that y is all of this, tangent 2x to x power, right? The original expression. So we simply replace y with what it represents. So in that case then, we have limit as x goes to 0 from the right side of tangent of 2x to x power equals 1. Okay, so there's our limit. Remember that we started out with an indeterminate form, but now we end up with a limit that converges to 1. And again, sorry about that. I will get rid of that before posting this. So it'll look clean by the time you see it on Web Campus. Maybe we should do more examples, but let me just make sure that there is no class coming in before we continue. If there is a class coming in, I'll just stop at this point, and we'll do more examples in class as classroom worksheet activities. But let me just find out if there is a class coming in, and we'll continue if there's nobody out here. But I heard door open and close, so I'm just going to check. Oh, there's nobody out here. Okay, so we can continue. Good. That way we can see more interesting examples here. Okay, so if we have time, that is, we'll do a couple of additional interesting examples. Again, please, I'm just going to remind you, please pause the video and have a go at this on your own, see where you end up, and then compare your solution with mine, and hopefully our answers agree. Okay, so I'm assuming you've done that, and now you're back. So if we apply the limit, what are we going to get? We're going to get 0, and of course, natural log of 0 from the right, it's going to be some negative infinity number. And this is an indeterminate limit, right? So indeterminate limit, apply L'Hopital's rule. Okay, I'll just grab another blue pen here. All right, so of course we're going to have to rewrite this in fraction form, right? So let's do that. So limit as x goes to 0 from the right, and I'm just going to put sine of x in the denominator. So natural log of x over 1 over sine of x. Okay, so we know that 1 over sine of x is equal to cosecant of x, right? So usually it's better to convert cosecant of x to sine of x in this form, or secant of x to cosine of x, to 1 over cosine of x. But in this case, we can convert this to cosecant of x. So let's do that. So knowing that cosecant of x is equal to 1 over sine of x, then we can rewrite this. So limit as x goes to 0, natural log of x over cosecant of x, right, like that. So let's apply the L'Hopital rule. And recall, this is important, recall derivative of cosecant of x is equal to minus cosecant of x cotangent of x. So just remember that. We're going to make use of that when we apply the L'Hopital rule. All right, so we have that. And then limit, so let's take the limit, and we're going to take the derivative of numerator and denominator. So that'll be 1 over x, right? And that one, we have that. So minus cosecant of x cotangent of x. And then limit as x goes to 0 from the right, So let's rewrite this so it looks a little bit neater. So we have 1 over x times 1, or maybe I should put this minus, I'll just put it here, and then 1 over cosecant of x times 1 over cotangent x. And recall that something that we made use of in the previous example, again, it comes up here. Recall that limit as x goes to 0 of sine of x over x is equal to 1. Remember that. And this came up in the previous example. So we're going to substitute. If we replace cosecant of x with 1 over sine of x, then it'll become apparent why we need this. So let me do that. So we have limit as x goes to 0 from the right side of minus 1 over x times 1 over 1 over sine of x. So this cosecant x is 1 over sine of x, and 1 over sine of x times 1 over cotangent of x. By the way, the tangent and cotangent are reciprocal functions, right? So 1 over cotangent of x is equivalent to tangent of x. So I'll just write it like that, and I will clean this up. I will clean this up later. And then what do we have? We have, there's a lot of rewriting going on here. Do you see that? Rewriting that in this term, rewriting that in this term. And so x goes to 0 from the right side. So this will be, so we'll have minus 1 over x times sine of x times tangent x. And then, of course, this is minus sine of x over x, right? And then if we take the limit of sine of x over x, we get 1. So it works out nicely. And so limit as x goes to 0 from the right of minus sine of x over x times tangent of x. Okay, so this will be minus 1 because of that. So we have minus 1, and take the limit of this as x goes to 0, we get 0, right? Because tangent is sine of x over cosine of x, and if sine, that would be, as you apply the limit, would be 0 over 1, so that's 0 again. And then, so this will reduce to 0. So there we have it again. We went, again, I want to remind you, we went from an indeterminate form of a limit to a result that converges to a number using the L'Hopital rule. And this is very useful for us. Okay. All right. So that's that example. Maybe I think we should do one more example and we'll stop. So here's another example. And please take your time, pause the video, take your time and work this out on your own before unpausing the video and seeing the solution from me. Okay, so I'm assuming you've done that, and now you're back. So that's great. So applying the limit, what do we get? We get a over infinity, which is 0. And then we get 1 to b times infinity. We get 1 to infinity power. And that's certainly in one of the indeterminate forms, right? Let me bring back that slide. You see that? 1 to infinity on the first slide, first page, we talked about it. So that's an indeterminate form, which means this expression is candidate for applying the L'Hopital rule. So indeterminate form, and we say we must use L'Hopital's rule. Okay, so again, we want to set, because this is in exponential function, right? And the last note that I had, what do we do exponential functions? We set it equal to y and take the natural log of both sides. We do what we have to do, and at the end, we apply the natural exponential function to convert it back to the y. So let y, let y be equal to all of that, 2bx power, right? So now we're going to take the natural log of both sides. Like that. And then let me take the limit of both sides, of course, to bring the limit here. Bring in the limit as x goes to infinity of natural log of y equals limit as x goes to infinity of b times all of that, right? B times natural log of 1 plus a over x, a over x, and then let's see. And then we have this x here, right? This x here, it's almost not even visible, but maybe I should add a little bit color to it. So this x, let's put it in the denominator because we're going to need to convert this in fraction form anyway. So that we will put, we can write it as 1 over x. So if you simplify this complex fraction back into this form, this x multiplies itself by b, all of that over 1, and we get this expression back. Okay, but we did this so we can apply the L'Hopital rule. I'm just double checking to make sure that everything looks good here. Yep, it looks good. All right, so now we apply the L'Hopital rule. L'Hopital rule. So we take the limit of, like that, of the left side, natural log of y, is equal to, we need to take the derivative of the right side. So b is a constant, it stays where it was. The derivative of this would be 1 over all of that, so 1 over 1 plus a over x, times, of course, by the chain rule, times the derivative of this, which would be, that would be a times, so I don't know if I can use, so that a over x, I'm just using a scratch paper here, a over x can be written as a times x to minus 1 power, and then taking the derivative of that would give us minus a 2 times x to minus 2 power, right? Or we can write minus a over x squared. So we can, that would be the derivative of that. So minus a times minus a over x squared. Okay? And then, of course, the derivative of this 1 over x is minus 1 over x squared. All right? So let me put that. And this will be minus 1 over x squared. So we can, so if you have, again, we're using a scratch paper, 1 over x is equal to x to minus 1 power, right? If you want to take the derivative of that, it'll be minus x to minus 2 power, or minus 1 over x squared, positive power. Okay, like that. So that's what you see here. And then let's clean this up a little bit. So on the left things look nice. On the right we have some work to do here. So we have limit as x goes to infinity, and then we have, so minus a times b, right? Minus ab, minus ab divided by, let's see, so x squared times all of that, x squared times 1 plus a over x divided by minus 1 over x squared. So I cleaned up a little bit, not much, this one, just from here to here. So let's clean it up a little more. So limit as x goes to infinity of natural log of y is equal to limit as x goes to infinity of, so now we have minus ab times x squared, right? Minus ab, we're getting rid of this complex fraction like that, divided by minus ab, so minus 1 times all of that. So minus 1 times x squared times 1 plus a over x. And then, of course, this. I mean, the easiest way to simplify a complex fraction is take the product of the farthest terms by each other. Take their product, put it in the numerator. Take the product of the nearest terms and put them in the denominator. And that's what I did. Okay? So this is minus x squared. Okay, now that minus and this minus cancel out. We get positive. So we have limit as x goes to infinity of natural log of y is equal to limit as x goes to infinity of ab over 1 plus a over x, right? So if you apply the limit at this point, what are we going to get? This term will drop out, right? This term will reduce to 0. A divided by infinity will be 0. 1 plus 0 is 1. AB over 1 is just AB, right? So we get limit as x goes to infinity of natural log of y is equal to AB. But remember, this is not the final result. This not yet the final result. Okay, we need to take the natural exponential function of both sides, and that will be the final result. So let me try to do it on this page. I don't want to go to a second page for this. It's better to keep the solutions on one page. So if we do that, we take, it'll be limit as x goes to infinity of e to natural log of y would be equal to e to ab. So we take the natural exponential function of both sides, and so this side will be y. So then from here, right? Again, I'm trying to squeeze everything in this little space so I don't have to start. So you have everything on one page, basically. So we get y, so we get limit of y, or limit as x goes to infinity of y equals to e to ab power. AB power, right? But y, remember y was equal to that, which is all that expression. So in the expression result that we have, let's replace y with its equivalent, which is that. If we do that, we're going to get limit of as x goes to infinity of 1 plus a over x to bx power equals e to ab power. So there you have it. You have this final result. using the L'Hopital rule. Okay. So again, this is nice because originally we had this, right? Without L'Hopital's rule, we had that, an indeterminate limit form. After that, we get convergence. We find what the limit is converging to, which is e to some ab. Depending on what a and b we choose, a and b are just constants. Whatever a and b, the limit of that expression will converge to that. Okay. I hope this was helpful. We will do additional examples in class using the classroom worksheets as usual, right? So I thank you for watching this video until the end, and if you solve these before you saw my solutions, that's just awesome, and that's what these videos are meant to be, just an auxiliary help in addition to what you're doing to solve these problems. So thanks again, have a nice day, and I'll see you again next time.